Welcome back, everybody. So today we are going to follow up what we did on Thursday, where we looked at the Hartree-Fock equations, and we prepared everything for studies of the ground state energy. Now, one of the motivations, again, just to repeat what we discussed, is that this is one of the few systems where we can find an analytical solution to both the ground state energy for an interacting system and for the Hartree-Fock energies. This gives also a very good first approximation to studies of properties of metals, especially for valence electrons in metals. And it serves also as a method which links the basic methodology, links well with the studies of infinite nuclear matter, as seen in neutron stars, or dense nuclear matter in heavy ion reactions at low temperatures. So these are systems where we've actually put temperature to T equal to 0. And there are many physical realizations of such systems which we can actually cool down to very low temperatures. So temperature is actually an effect which we have neglected here. So these are electrons or particles governed by the Fermi-Dirac distribution at temperature equal to 0. Now, today, we are going to look at the derivation of the ground state energy of the electron gas. And that is going to give us, after a long detour, and there are some technicalities on how you can actually evaluate these integrals, which I wanted to convey, because some of these integrals, the way we calculate them, it's actually useful to have seen it. Because if you move on to studies in atomic physics, molecular physics, or condensed matter physics, it's often useful to have seen how you arrive at these equations. Instead of just saying that, okay, I accept that you get this, but from an intellectual point of view, I think it's actually very useful to understand where the equations come from. And at the end, we are just going to get an equation for the energy from the interacting part of the Hamiltonian, which is going to be given by a constant times the density of the system to the power of 1/3. And this serves as an input to density functional theory, which is a widely used many-body methods. It's a mean field methods, but it's widely used in material science, in condensed matter physics, in atomic, molecular physics, and nuclear physics, and essentially all fields of low energy physics. And for those of you who may dive into material science, this is actually one of the more popular many-body methods. And there is a huge community which has developed very efficient codes. Some of them you have to pay a license to use. So the Center for Material Science uses a code which is called WASP, V-A-S-P. And they typically pay a license price of something like 100,000 kroner per year. And that is highly streamlined to high-performance computing facilities. It has a lot of functionality. You can look at many different types of materials and extract properties like the band gap we discussed yesterday, or the energies of the system, etc., etc. So these are, for those of you who are interested in density functional theory, we do also have a course which deals with running density functional theory codes and apply this to specific systems in material science and condensed matter physics. We will probably just scratch the surface here or just link to literature, and then this will be the topic next week. But then I wanted also to spend some time on the midterm and just say some few words about that one. But let's quickly remind ourselves about the electron gas. So this is perhaps the only realistic model of a system, one of the few ones, where you can, for many interacting particles, you can find an analytical solution for the ground state and the Hartree-Fock equations. So just a quick reminder of what we did yesterday. So the system as a whole is neutral. So there is a uniform background of ions or molecules or atoms, which then balance the charge which is set up by the electrons. And we assume that these ions just provide a uniform charge which has a specific density here. And that is the contribution from the background ions. Then, after that, we can, what we did, we went through the setup of the Hartree-Fock equations. And the assumption is that we can use plane waves. So we are looking at a system in a box. And this system in a box here, for a non-interacting system, has as eigenfunctions these so-called plane waves, where we have a wave number or momentum, as we loosely call it, because we put often h bar equal to 1. H bar times the wave number is equal to the momentum. And we loosely call this K for momentum. And at the end, when you look at many of these equations, we would use something which are called either atomic units or natural constants. And natural constants means that all the physical constants are put to 1. And then you have to figure out how to bring them back again. And that is always a recipe for confusion. So you're scaling your equations, you make them dimensionless, and then you have to recover where the right dimensions have to be put back again. You've probably seen cases like that. And then we have a spin dependence, though the Hamiltonian itself is spin independent, which means that when we calculate the expectation values, then we have to have the same spin on the bra side as we have on the ket side. And you can easily see that, because if you try to multiply the transpose of this one with this one, that becomes immediately equal to 0. And as you know, we always skip the tensor product notation, but we actually have a tensor product between the spatial part of the wave function and the spin part. But this is normally skipped. And then just a quick reminder, when you look at solutions in a box, then the momenta get discretized. And these quantum numbers Ni, as we discussed yesterday, they take values from 0 to, in principle, plus minus infinity. So we have a particle in a box with an infinite set of single particle states. And then yesterday we also defined the Hamiltonian, and we calculated the kinetic energy. So this is a system which has kinetic energy plus some interaction piece. So that's the electron-electron part. But the Hamiltonian itself is going to contain an electron-electron repulsion. There's going to be a background from the ions. And then the electrons also interact with the background. Now, today, what we are going to see is that this part here produces a term which cancels exactly these two terms in the limit of an infinite volume. And then we are going to be left with a simpler term for the electronic part and the Hamiltonian itself. And this is something which we can evaluate. So when we talk about in physics, what we call the thermodynamic limit, we are running calculations in many, many cases with a finite number of particles and a finite volume for the box, which confines the motion of the particles. But then, since this is an infinite system, we would obviously like to take the limit of an infinite number of particles. The density is constant, but the volume and the number of particles go to infinity, but their ratio is a constant. And that means also that the energy per particle is a constant. The energy is what we call in physics an additive quantity, and it depends as a function linearly of the number of particles. Then this is these are the equations which we're going to look at. So this n here now represents the wave function squared. And yesterday we saw actually that this quantity here, if we take the wave function squared, the bra side and the ket side, we can then define this density. So we are simply thinking of the two ions which interact with each other in terms of a fixed density here. And that means that we can pull out a term like this, which is just a constant, and where omega is the volume. And then there is and this term which we have here, this is a convergence term, which we introduce in the equations in order to be able to actually calculate the integrals. because when I calculate the integral for this Coulomb interaction, if I don't put in this convergence factor, this is going to give us an integral which will give rise to divergences. But then when we have the final expression, we are going to take the limit of this mu going to 0. So that's a calculational trick. However, for those of you who study nuclear physics, the interaction between nucleons has often a term like this one, because the force has a finite range. So this is a way to bring in a finite range of the force. So when Yukawa got the Nobel Prize in physics for having introduced the pion as a first model for the nucleon-nucleon interaction, people knew from experiment that the interaction had a finite range. So this term here, depending on mu, will obviously make the interaction go to 0 at a certain distance, because you have this factor which we normally call a damping factor. Now, in atomic physics and condensed matter physics, etc., this often is something which people call a screening factor. So the Coulomb interaction is mathematical in principle, a force which has an infinite range. But then with such a screening factor, you actually dampen the infinite range of the force. And you can think of that in a physics-motivated way, in the sense that if you look at a particle which interacts with many, many other particles, the background is going to set up an effective force, which means that the force will not have the infinite range as we would expect if we had just two isolated electrons or two isolated charged particles which interact with each other through an electromagnetic force. And the background charge and the electrons is something which we would now sum over all the electrons. And this is the this xi here is the position of a given electron, which then interacts with the background. And this is also a quantity. So these two quantities here, they're actually going to be cancelled by a contribution from this term here. And we are coming back to that a little bit later. So yesterday, what we looked at was the calculation of the Hartree-Fock energy for the single particles. And what we found was an equation which looks like this. Now, this equation is at the Fermi level, does not diverge, because when you take the limit, when k is equal to kf, there's going to be a term here and a term from the log term, which actually will balance each other. However, the derivative diverges at the Fermi level. And this has some consequences for interpretations in many-body theory, which I will say a little bit about after we have revisited what we found yesterday. So when we are calculating these integrals, what we did then, we found this term here. And then yesterday, we spent a good fraction of the lecture actually deriving this term. And the trick which we used then, which you may have seen in textbooks on condensed matter physics or statistical mechanics, is that the finite number of over sum over the momenta which the particle can access is replaced by an integral. So this is in the infinite limit. So we have the convergence factor, and when we had the convergence factor here, we could actually calculate that integral. So if you scroll down here, you will see some of the calculational details which we went through yesterday. So I'm not going to repeat them, but I'm actually going, so this contains basically all the derivations we did. And the thing we did was to rewrite everything in terms of physical constants. So one constant is the radius of a sphere, which represents the volume per conducting electron. So that is something which we will relate to the density. So the density is given by the number of particles divided by the volume. And I see that I have mixed, sometimes I call the volume for omega and sometimes for V. I saw that now, sorry for that. So sometimes you think V and sometimes you think omega. I have to correct this in the notes here. Sorry. I saw it first now, actually. And this sphere represents the volume per conducting electron. And then you could rewrite this equation here in terms of this function which we defined here. And if we divide by the non-interacting contribution at the Fermi level, so which is just kinetic energy, then we arrive at this equation here, which is the one you will often see in the literature. And it's pretty common to rewrite this in terms of the Bohr radius. And you would also rewrite Kf here in terms of this radius of a sphere, which is the volume a specific electron occupies. And that relates also, again, to the density of the system. So you will often see the results being given. So if you use this quantity here, then you will find that Kf is given by 1.92 divided by Rs. And it's pretty common to rewrite this equation like this. So then you have introduced physical constants, and the A0, which is the Bohr radius, is often used as a natural length unit for atomic systems and condensed matter physics and molecular physics. And that gives you a typical range of what you may expect could be the size of an atom or a size of a molecule. And the Bohr radius, when you bring it in here, is just defined by natural constants. And in most metals, this Rs is something like 2 to 6. And in the code which you see here, what I've done now is to define something which you will find in textbooks in condensed matter physics, and it's called the band gap. And we will call the band gap we will define it using the Hartree-Fock energies. So we call this the Hartree-Fock band, which is then the difference between the energy at the Fermi level and the energy at k equal to 0. And in this specific case, if you now take the Hartree-Fock result and divide it by this one with the unperturbed energy, just kinetic energy or the non-interacting energy, then we have a 0.326. And then if we look at the Hartree-Fock equation and take that one at k equals 0, then this ratio is minus 2.652. And then we can make a plot. And this plot here looks like this. And you see now that you have a slight discontinuity due to the log term at the Fermi level. And this means that when you take the derivative of this quantity, you will actually get a logarithmic divergence. And the reason why I bring this up is that it's pretty common to, in many body physics, to redefine something which we call the effective mass. So what we're going to do now shortly is actually to take this equation which we have here, this one, and make a Taylor expansion around the Fermi level. And that introduces something which is called an effective mass, which is then related to the higher order derivatives. You know that when you make a Taylor expansion around a quantity, you have the first derivative, the second derivative, etc., etc. And the first derivative is obviously going to be given by the derivative of this epsilon k Hartree-Fock. So this is just a technicality which you will often encounter in many body physics. And especially when we come to perturbation theory and approximative many-body methods, there are ways by which you can recover a finite effective mass by adding higher order many-body terms. So what you see then, again, is just a plot of these equations. So this would be the nice curve here. The red one is just the non-interacting system, just the kinetic energy. And it's obviously 0 when k is equal to 0. And then we have a gap here. And the distance between the Fermi level and the lowest lying state when k is equal to 0 is something which defines the band gap in condensed matter physics. So that's the energy you require to excite the system above, or just to knock out one electron above the Fermi level. So if you now think of this, all these states here, as representing now a continuum of states, because we have assumed now that k takes continuous values. In the beginning, when we looked at a particle in the box, we had discrete values of k. But now we have gone into the thermodynamical limit, and we assume now that this k takes a continuous set of variables. So K equals 0 would be the lowest lying state below the Fermi level. And then we keep adding K values till we reach the Fermi level. So this would be the states which occupy all the single particle states below the Fermi level. And then the gap which you see here between 0 and the Fermi level is the energy which is then required to excite the lowest lying electron above the Fermi level. So the band gap is an interesting quantity because you can actually extract information about the band gap from experiments. And at the Center of Material Science, we do actually have experimentalists who have specialized in extracting information about the band gaps in materials. And then you can relate directly your many-body physics to what they see experimentally. So just keep in mind that single particle properties are not observables. This is the many-body system. So what we are extracting is an interpretation. So the Hartree-Fock energies are the mean field energies which we are using to model the system. But when you calculate or you make an experiment, the observables you have are not single particle properties, but it's actually a many-body system you observe. And you make a measurement on that, and then you have to relate the measurements to the theory, the underlying theory. So that's a long way to go, actually, which we will not discuss here. But what I'm just simply stating is that these quantities here can actually be related to experimental quantities. Okay? So that's a kind of long detour here. This effective mass is an interesting property because many people have dedicated years in order to find a better approximation to the effective mass. Now, one of the problems which you see here is just an artifact of the calculations. So the artifact here, if we now just switch quickly back to the whiteboard. So it is a calculational artifact in the sense that if we go back to the Hartree-Fock equations, so one of the things you can do, there are several ways of solving the Hartree-Fock equations. So if you think back at the Hartree-Fock equations, what we found is that the transition from the ground state to a one particle, one hole excitation is something which when we use variational calculus, if we use variational calculus, then we can put this one to 0. And that was given when we translate a many-body state and plug in the Slater determinants, then we could actually rewrite, if this is a state like this, we could rewrite this in terms of specific matrix elements or integrals, which have to be equal to 0. So one way to solve the Hartree-Fock equations is then to require that A of F of A is equal to epsilon A, Hartree-Fock. We could also take states below the Fermi level, and this is the way we actually implemented it in the code, and which you can implement also in the project. And feel free in the project or the midterm to actually use the codes which we have put forward. So this is normally what's called the standard Hartree-Fock. Some people call just a canonical Hartree-Fock. But what you could also do, because this also has as a consequence that IFA is going to be equal to 0, which means again that if I take this new basis here and take the overlap between I and A, that is equal to 0. Now, an alternative here is simply to say that this specific operator which we have, this F, which includes the kinetic energy, is only equal to non-zero for the states below the Fermi level. That's another way to implement the same equations, because the only thing you want to fulfill is this relation here. And you can fulfill that one with either this recipe, or you can fulfill it with this recipe. So there is nothing which hinders you by stating that this is the energy which we want to obtain, and this is the way we want to obey this relation here. Now, what happens then is that the expectation value of this quantity is 0, but that doesn't need to mean that the single particle energy is 0. Because in this specific case, the single particle energy of the system, for this specific system, it means that the state A is given by kinetic energy only. So for the electron gas, if we go back to that one, it means that epsilon of A is just going to be given by h bar squared of this momentum Ka divided by 2m. So we have kinetic energy only, because we are putting the Hartree-Fock equations to be 0, but this particle does have kinetic energy. So this is just a recipe which you can implement. Now, this is going to give us a discontinuity at the Fermi level if we implement this recipe here. And this is what we see in the equations. So we could have required that above the Fermi level, we do not put this one equal to 0, but the way the electron gas is set up, in our case, leads to the second choice for the Hartree-Fock equations. So if you then go back to the equations here, which we have in the slide, you see now that what kicks in here is actually the kinetic energy. So the kink here is where the term below the Fermi level kicks in, and then we have simply just kinetic energy after that. And this gives this small kink here. So you can actually avoid that kink if you add complexities to the solution of your one-body problem. Now, if you look then at this, what you will have is an artifact. If you now make a Taylor expansion for K near the Fermi level, that means that you have the first derivative and then you have higher derivatives. What is common to do then is, now if you look at the non-interacting system, then the non-interacting system is pretty trivial. That has just the derivative of the kinetic energy. So I'm looking at the derivative of the energy, and it's common to actually, in many-body physics, to rewrite this term, which you see here, as an effective mass, where you define the effective mass in terms of h squared kf times this derivative here. So that defines an effective mass, because if you look at the equation which you have here, so this plays the same role as a momentum squared divided by mass. So that's what we would expect when we think of the energy of a system, the kinetic energy. So this is a modification of the kinetic energy due to higher derivatives. And what I have as an exercise is actually to show that this effective mass can actually, when you compute it, you can actually show that the level density, the number of single electron states per unit energy, can actually be written like this quantity. And if you run these calculations, then you can ascribe the fact that this term here is going to diverge, because if I now take the derivative of the energy here, we will get a divergence at the Fermi level. So this divergence has to do with the fact that we are dealing with the long-range part of the Coulomb interaction. So this is actually a small exercise which we will look at after we've done with the midterm. And there are some interesting physical properties which relate to the Coulomb interaction and its infinite range. If you add some screening to the Coulomb interaction, then this divergence of this term here will actually disappear. And this is something you can also improve upon from a calculational point of view by adding higher order terms to the effective mass in perturbation theory or Green's function theory, as we will see a little bit later from now on. So this is just to anticipate a little bit what is coming. Now, what we are going to do now is actually to look at the calculation of the ground state energy. And just to quickly remind you, these are the terms which we have. And we discussed that yesterday. And we are now going to look at the energies in terms of creation and annihilation operators. And we're going to set up the final energies which we need to compute. But now we go back to the whiteboard. So I wanted just to do this longer digression to bring up what we did yesterday and link this to the calculations of the ground state energy. So let's do that. So the ground state energy and let us set up the specific ingredients which we need now. So we are going to assume that the total Hamiltonian is given by the kinetic energy of the electrons. So I'm going to put an E here, and then I'm going to drop it because the kinetic energy is going to be related with the electrons. Now the ions are at rest. So they don't contribute to the kinetic energy of the system. So that's why I'm going to drop the subscript E in the next equations. Then there is going to be a piece which is the electron-electron interaction. So the two electrons repel each other. And we have the term, which is V electron background, so B for background, plus a term which is the two background ions interacting with each other. So we're going to look at these two terms a little bit later. So let's just look at these two terms here. So these two terms are terms which are going to be equal to, so this first term is equal to I from 1 up to the number of electrons which we have. And then I'm going to have an h squared of ki divided by 2m. And now I'm thinking of this system as a system in a finite box. Then what I have is a plus, and we have a repulsive term with e squared. And I have a sum over all the electrons, ij, up to n. And I'm introducing this convergence factor because I'm going to later to take the limit, lim of mu goes to 0 later. So I'm introducing this as just a convergence factor in this integral. And this is going to be given by Ri minus Rj divided by Ri minus Rj here. And in this particular case, I've put some of the physical constants in the Coulomb interaction to 1. I'm just putting in the charge here. So what we are going to do in order to make these integrals well-defined, we are going to look at the limit of n goes to infinity and n goes to infinity. And we're going to make an assumption that we take first these two limits. This ratio, the density of particles, n divided by the volume, is assumed to be constant. Also, this volume is now given by the length cubed of a box. So this is L side of a box in 3 dimensions. So I don't need to repeat that one. And we are going to assume now that this quantity mu times L is much smaller than 1. Okay, so in the calculations now, so let's take a look at the Hamiltonian now. So here, when we looked at this expression here, let's take the kinetic energy first. And we are going to rewrite this in second quantization because at the end, we're actually going to deal with second quantized operators. So if I take the energy here for the kinetic energy, so this term I equal 1 up to n of h squared ki squared divided by 2m, we are going to rewrite that in terms of a second quantized term. And in this case, we are now summing over all the possible single particle states. Now, of plain sloppiness, in order to avoid equation or clutter with equations, I'm going to skip vector signs simply because that's just going to give a lot of clutter in the equations. But in our case, this k, they represent three-dimensional vectors, which take discrete values with different quantum numbers. And then I also have the spins of particle 1 and the spin of particle 2. So if I now use the operators here, I have a k1. In principle, it should be a k1 vector, but I'm going to skip that simply just to avoid a lot of clutter in the equations here. So I have a k1 and sigma 1. And then I'm having the kinetic energy operator T here, which I indicate like this, of K2 of sigma 2. And this contains a creation operator of K1, sigma 1, dagger, of A, K2 of sigma 2. So this is the corresponding operator in second quantization. And yesterday, what we found is that these matrix elements are actually K1, sigma 1 of T, of K2 of sigma 2 here, they have to be equal to a Kronecker delta of sigma 1, sigma 2, because the kinetic energy does not act on the spin degrees of freedom. And then I do also have a delta K1, K2, and then I'm simply having an h squared of K1 divided by 2m. Now, the spin degrees of freedom are pretty obvious because the kinetic energy does not act on the spin degrees of freedom. So if you have a spinor, which looks like this, and this one is given by 0, 1, then you see that this is automatically 0. So that means that I can rewrite the kinetic energy operator. So in second quantization, I can rewrite simply as a sum over k and sigma, and then I have this matrix element, which I now just write as h squared of k squared divided by 2m, and this contains an ak sigma dagger ak sigma. And then when I'm now going to calculate expectation values, I will obviously change this one to a sum, an integral. So if we now look at this specific term here, we can rewrite it because it has two spin degrees of freedom, either spin up or spin down. And there is no term which involves spin in the Hamiltonian. So I can actually rewrite this in terms of a sum over k of h squared, k squared divided by 2m of ak, and I can leave out the spin degrees of freedom. So I'm simply summing up over the spin degrees of freedom. So there's a degeneracy due to spin. So every state k which I have corresponds now to a state which has a double degeneracy. So I can have a spin up and a spin down. So if you now think of this three-dimensional case which we had, so if you go back in 3dim, what we had then is a state where we had the energy equal to 0. So we had this n1 squared plus n2 squared plus n3 squared, as we discussed yesterday, which is equal to 0. And in that case, this corresponds to n1 equal n2 equal n3 equal to 0. So this state can now host two electrons, one with spin up and one with spin down. So we have 2. Now, when we then went up 1 excitation unit, when this N1 plus N2 squared, so the energy is proportional to these quantities when we are looking at discretized values of K. But then we are going to take the limit where K becomes a continuous variable. But in this case, we had 1 here. So then we had 6 possible combinations. So we had N1 equal to -1, N2 equal to N3 equal to 0. And this has also these states. And then we had plus 7 more. No, I think it was 6 more. I don't remember. I think it was 6 more, yeah. But then we end up with 12. So it's actually, yeah, in total here, we actually have 6 possibilities. And that means that we have a 6 times 2, which gives us 12 slots for the single particle states, plus 2 from the lower one, gives us then, so this is actually plus 5 more. So for this specific case, with N1 squared plus N2 squared plus N3 squared equal to 1, we can now place 12 particles. And 2 plus 12 gives 14, so 14 becomes the next so-called magic number where we fill all the single particle states up to the Fermi level. And then we could continue like this with 2, 3, etc. So it means that when we now are filling in this specific case, this sum runs over the number of particles which we have defined. So if we have 2 particles, then we obviously have only N1, N2, and N3 equal to 0. If we have 14 particles, so here we get 14 in total. So this gives us 12. 12 plus 2 is 14. And then you would continue. So the next one was 38. And then we have 56, I think. And then 66, no, 54, 66, 114, etc. Okay, so let's now calculate the kinetic energy. So what we are interested in is phi 0 of what we will call H0 for the electron piece. So H0 is just the kinetic energy operator, which is often written in terms of a T here. And we are going to replace the sum which we have with an integral. So this sum is actually going to have a factor V when we introduce the wave function. And this will be now given by a 3-dimensional integral. So what we get then, when we are now calculating the expectations values, when we introduce the creation and annihilation operators, we know that this state K here has to be below the Fermi level, because if not, it's going to be 0. So just remember now that and we've done this many times. So phi is simply the product of all these states, I equal 1 up to n of a I dagger acting on the true vacuum. So I'm not going to repeat the calculation of that because we've done this type of calculations many times. So this means that when I now plug everything in here, this quantity phi 0 of the kinetic energy is simply going to be given by a factor of 2, which is the degeneracy we had due to spin. And then we have a volume element. We get an integral from here because there is no angle dependence in the kinetic energy. So if we now look at the integral which we have, this is going to be given by 2, and we integrate out the angles divided by 2 pi cubed. And in this specific case, what we have, so we were missing this factor of V here. So we have to multiply with that factor of V. And then we have an integral from 0. And let's do that one before we take a break, up to the Fermi level. And K squared. So this sum actually runs up to the Fermi level. So we have a K squared dk. And I have an H bar squared of K squared divided by 2m. And if I do the integral, what I get is V times h squared divided by pi squared of 10 times m times kf to the power of 5. And then it's common to rewrite this in terms of the number of particles and the density. So if we now look at this specific contribution here, let's do that, if that is okay. Everybody's written it. So we now simply introduce this n divided by v, which is something we calculated yesterday, which can also be defined in terms of the Fermi level. And this is 3 pi squared. And we can rewrite this one in terms of the volume which a single electron occupies with a radius rs. And if we do that, then I can rewrite this phi 0 of h0 of phi 0. This can be rewritten as h bar squared times the volume divided by 10 of pi squared times m. And then I have 3 pi squared times the number of particles divided by v. Now just replacing the Fermi level to the power of 5/3. And this is then given by 3 of h squared of 10m. And then I have 4 pi divided by, it's actually divided by 4 to the power of 2/3. And then I have n divided by rs cubed. And if I divide by the number of particles, what I will have then, and this is pretty common to do it because n goes to infinity, we're going to take the limit n goes to infinity, which means in turn that we have to get rid of this one by simply taking the energy per particle. And then we are just left with the constants, which we have to plug in. So the energy per particle then is simply given by some physical constants and some other parameters, which are just given numbers, rational numbers. And if you introduce A0, let me just do that before we take a small break, divided by, this is the Bohr radius, this is the mass of the electron, multiplied with the charge. Then we can also introduce a unit which is widely used in condensed matter physics. It's called the 1 Rydberg, and that's given by m of e to the power of 4 of 2 of h to the power of 2. And this corresponds to 13.6 electron volts, which is the energy of the hydrogen atom in its ground state. So that defines a unit which is called 1 Rydberg. And then we can actually rewrite this energy of phi 0 of h of phi 0. And if we then look at the equations we have plugged in and divide by the number of particles, this is going to be equal to 2 times 21 of A0 divided by Rs cubed. No, squared. I think it's squared, yes. Yeah, it's squared, multiplied with 1 Rydberg. So that's the energy. And that gives us a very compact expression for the energy per particle. And it's then defined in terms of a natural length scale and the radius of the volume which a single electron occupies. So we have then a pretty natural length scale which relates to the density of the system. Okay, so that was the kinetic energy. And I went a little bit over time. I wanted to stop there. And after the break, we are going to look at the contribution from the Coulomb interaction. So let's do that. So this is a kind of technical digression, but it's useful to have seen it because if you deal with similar systems, you know exactly what kind of integrals you need to deal with. We'll take a small break. Questions? I guess people need some coffee or something else too. I need a coffee. So what we did before the break was to calculate the kinetic energy. Now, the next element is the interaction piece. So let's now look at the electron-electron interaction, only that piece. And if we go back to where we started, we made an assumption that we have a Hamiltonian, a total Hamiltonian, which contains some input from the electron background and some from the background. So these are the ions. And then we have a standard electron-electron piece, which we actually rewrote like this. So let's take a closer look at what this one looks like in second quantization. So if we move to second quantization, we know that this term, the interaction piece, so the electron-electron piece in second quantization is going to be given by 1/2. And then I have a sum over K1. And again, I'm going to skip the vector signs, K4. And then I have a sigma 1, sigma 2, sigma 3, and sigma 4. And we have a integral, which now relates to these single particle states, K1, sigma 1, K2, sigma 2. There is an interaction. And then I have a K3, sigma 3, K4. This is K4 and sigma 4. And this is multiplied with an A, K1, sigma 1, A, K2, sigma 2, and A, K4, sigma 4, and A, K3, sigma 3. So this is the operator in second quantization, which we're going simply to use to calculate the expectation values from the ground state to the ground state, which is now simply given by this assumption about the Fermi vacuum. Now, if we now look at the matrix elements, which we have to deal with. So the term which we call K1, sigma 1. So let's just look at this integral or matrix elements, as we often call them, because that's going to reduce some of the summations which we have here. Now, if we look at this one, this translates into obviously integrals and spin terms. So a K1 sigma 1, this is going to have, when we now write it out, there's going to be a spinor, which I just write as sigma 1 here, complex conjugate, particle 1. There is going to be a spinor for particle 2 here. And then this is then multiplied with x sigma 3, which is this is not an x, it's a xi. And xi for particle 1, and xi for particle 2. So I'm just writing out what this looks like in spin space and in coordinate space. Here we have, I'm just looking at the specific element, but just keep in mind that we do also have a summation here over the spin values. Now, the thing is that when you now look at this one and that one, this clearly tells you that sigma 1 and sigma 3 have to be the same. So the spin part is actually pretty easy, but let's now write out the spatial integral as well. So what we are going to have then is an integral over a dx1, dx2. And now you have to forgive me for being sloppy with vectors, and because these are three-dimensional objects, but I just write them as an x1 and x2. So this is just simply to avoid a clutter with notation here. And then we have a wave function, the spatial wave function, which are actually plane wave functions. So we have a K1 complex conjugate, x1, and then I have a psi K2, x2 here. And then I have the interaction, which is now set up here without any, so if we now put in the interaction, I'm actually putting some of the constants equal to 1. And then I have the absolute value of x1 minus x2. This is the interaction. And this is multiplied with K3 of particle x in x1 and multiplied with K4 of x2. So this is the integral as we defined them in the very beginning of the semester. So if I now look at the spin part and the spatial part, and I plug in plane waves, as we did yesterday. So if I plug in plane waves, this is going to be equal. So I'm having a psi of k of x, which is going to be given by 1 divided by this volume element of e to the I. And now I'm writing this without the vector signs, but in principle, there should be a vector here and a vector here, okay? But I'm just dropping it. So what it means, if I take this as an aside, is that I'm going to get delta sigma 1, sigma 2, delta sigma, no, so, sigma 3, and delta sigma 2, sigma 4. So they have to be the same. And then I have E divided by the volume squared, because I have 4 plane waves, and each one of them has a 1 over square root of V. So I get a V squared. And then I have the integrals dx1, dx2, and this is now multiplied with times. I get the E of minus I, and then I have a K1 minus K3 times x1. And then I get an E of minus I of K2 minus K4 multiplied with x2. And this is divided by x1 minus x2, the absolute value. So what I'm going to do now is to look a little bit closer at this specific integral and what we can expect from that one. So let's just look at the spatial integrals. So we have a dx1, so double integral, dx2 here. And let's just look at these terms here. And I'm going to rewrite it slightly. So I have a minus I of, I'm going to rewrite it like this, minus K4 times x2 minus x1, and multiplied with 1 divided by x1 minus x2, and multiplied with E of minus I, and then I have a K1 minus K3 plus K2 minus K4 times x1. As a reason why I'm going to write it like this, because then I can actually make some manipulations here where I now introduce a y variable, which I call for x1 minus x2, and I introduce a new variable x, which is equal to x1. That is going to give me an integral which looks like dx1, dx2 here, and then I have an E of I of K2 minus K4 times y, and I have an 1 divided by y, and then I have an E of minus I, and then I have K1 minus K3. There should actually be a minus here. No, sorry, it's a plus here because I defined y to be x1 minus x2. So this has a plus K2 minus K4 times x. The next thing I do is to introduce this convergence factor, and I'm going to take the limit where this convergence factor goes to 0. So I introduce an E to the minus mu times y. And later we are going to take the limits. So let's now look at what we have here. If you look more carefully at these integrals, there's an integral over, sorry, I was a little bit rushed here because I changed the variables. So this should be an integral over dx and dy here. Sorry for that. You look at one line and then you write the other line on the whiteboard. So when you look at this integral, when we introduce this convergence factor, what we are going to have is an integral dx and dy. And then I have an e of I of k2 minus k4 times y of e of minus mu times y divided by y multiplied with e of minus I of k1 minus k3 plus k2 minus k4 times x. Now, the integral which you have over x here, if you multiply that one, the 1 over x, and this term here, just gives us the definition of the Kronecker deltas. So that's just another way of defining them. So that means that if I now also bring back these constants which I had of e of v squared, this quantity here is now the same as e squared divided by v, because 1 over v and the integral over x here gives us now a Kronecker delta where I have a delta of k1 plus k2, k3 plus k4. And this is multiplied again with the integral over dy. I don't need to put the x here. dy. And then I have my e of I of k2 minus k4 multiplied with y and multiplied with e of mu of y divided by y here. So if I then redefine a term which I call for q here, which is k2 minus k4, then the integral which you see here is actually a famous integral which we can evaluate because we have this screening factor mu or damping factor or convergence factor, whatever we might call it. So what we get then, if I introduce this variable, then this is going to be equal to e squared divided by v. And then I have the Kronecker delta, k1 plus k2, k3 plus k4. And this is going to be multiplied with 4 pi. So that's the integral of mu squared plus k squared. Now q squared, sorry. Okay, so still a long way to go here. Now, if we now look at what we have, so we actually do have a requirement on the variables k1, k2, k3, and k4. So in principle then, if we now bring back the vector signs, this is the same as us requiring conservation of momentum. And let's write this now in terms of a Feynman diagram. So you can now think of this as a physical process. If we just write it as a diagram, then it's often easier to see what is going on here. So if we look at the matrix elements we have been looking at, so we have a K1 here, we have a K2, we also had a sigma 1, sigma 2, and sigma 3, which we're leaving out. And then we have a K3 and a K4. So what we are saying now is that the momentum of the two incoming particles has to be equal to the momentum of the two outgoing particles. So what we are requiring here is actually a momentum conservation. So this goes also back to what I said yesterday without a proof, that these plane waves, since the interaction is translational invariant, they are also solutions to, they are solutions of the kinetic energy operator. They are also the eigenfunctions for the plane wave system here. So if I do this now, I can now do some further manipulations. So I'm going to rewrite, so I have Q2 minus Q4, which I rewrote in terms of this vector Q. I can now redefine a K1, which is equal to K3 minus Q. This is nothing but the same condition, if you just look at it, what we have there. I can rewrite now, if I define a new quantity, which I'm going to call for K3, so I'm going to change that one to a quantity P. So I'm going to simplify my notation here by just bringing in P and Q here. So these are now different variables, which now represent K3 and K4. So that means that I can rewrite K1 as K3. No, sorry, not K3, but as P plus Q. And I can rewrite K2 as K minus Q. So these are just manipulations of the equation which I'm going to set up now. So what we had in addition was a Kronecker delta. So I had a delta sigma 1 of sigma 3, and I had also a delta of sigma 2 of sigma 4. So that means that the equation which we looked at originally, which was this term here, this is something which we now can simplify. So let's plug in that expression and put in all the different Kronecker deltas and the new variables. So I can then rewrite that Hamiltonian or that interacting piece in the following way. So I get a V electron, which is now going to be given by a factor E squared divided by volume. And then I have this factor over half. I have a sum over the two spin states, sigma 1 and sigma 2, because I have a Kronecker delta on the spins. And then I'm going to have a sum over these variables, which I'm going to call for P, K, and Q. And then I have a 4 pi divided by mu plus Q squared. And this is multiplied with the creation operators, where I'm now going to have a P plus Q, which was K1 of sigma 1 dagger. And then I have an A of K minus P, which was K2 of sigma 2 here, dagger. And then I have an A of K, which was K3, no, K4, and then sigma 2 here, and then A of P of sigma 1. So that's my new operator. Now, what I can do next now is a further manipulation, because what you see is that if Q is equal to 0, I'm going to get a term which is just 4 pi divided by mu squared. So I'm going to single out a term here which goes like E squared of V of 2, and then I have a sum over sigma 1, sigma 2, and then I have a sum over P and K, and this is now given by Q equal to 0. And then I have a 4 pi divided by mu squared, like that. And then I'm just going to put in an equality sign here, except that now I'm putting Q equal to 0. So Q equal to 0 in these equations which you have here. And then there's going to be a new term, which has E divided by V times 2. And then I have a sigma 1 of sigma 2. And then I'm going to have a sum over P, K, and Q, but Q different from 0. So I'm just picking out the 0 term. And then I'm going to have a 4 pi divided by mu plus Q squared. And then I have the same terms as before, but now I have a condition that Q is different from 0. Now there's something which becomes interesting, which I'm just going to state. And this term which you see here, this can actually be rewritten. So the first term. So I'm not going to go through all these derivations. You will find more of that in the lecture notes, because what I wanted to do is actually to calculate the expectation value of this term only. So when you look at this specific term here, that is a term which can be written in terms of the number operator squared and minus the number operator times constants. So the first term, I'm just going to state that one. That gives us E squared divided by 2V and 4 pi divided by mu squared multiplied with the number of particles minus n, the number of particles, n squared minus n. And you can see that because if you take the creation and annihilation operators, so if you take these operators, so we have put now Q equal to 0. So what you will have then is an operator where you have P dagger. So let me just write this down for you. And then I have a sigma 1. And then I have an AQ sigma 2 dagger. And then I have an A of Q of sigma 2 and A of P of sigma 1. So when Q is equal to 0, this is the set of creation and annihilation operators which we have. Now I can now use the anti-commutation rules of fermion operators. So I can interchange this one with that one, and then I can interchange this one with that one. So I can actually show that I can rewrite this one as, so when I do the summation here, so I have a summation over P and Q and sigma 1 and sigma 2, I can actually, when I use the anti-commutation rules, I can rewrite this one as a sum over sigma and k, where k is now just a dummy variable. And then I have an A of k sigma of A of k sigma squared minus, and then I have a sum over sigma k and AK sigma of AK sigma. And this is the number operator squared, and this is the number operator. And these terms are multiplied by these constants here. So when I then take the expectation value, this one is just going to give me the number squared of particles, and this is going to give me the number of particles, which then translates into this quantity here. Now, these two quantities, they cancel in the limit n goes to infinity and v goes to infinity. They cancel the terms from the electron background and the background interaction, which I haven't calculated, but you will find these expressions in the notes. So this this term cancels exactly the H electron background plus the H background. So I haven't shown that, but you will find that inside the lecture notes. So what I want to do now is to focus on the last term here, which is this term here, because that's the one which is going to give rise to the energy of the ground state of the Hartree of the with a Hartree-Fock basis. So what we need to calculate then is actually the expectation value, the vacuum to vacuum expectation value. So if I now take phi 0 of V electron of phi 0, this is just going to be the vacuum to vacuum expectation value of that specific quantity which we put up. So it means that what we are going to look at is, if we now take all the constants in here, so we're going to have a factor of 2 pi of E squared. And I should now, let me just bring up one thing. There's one thing I wanted to add here. Let me just. Yeah, there's just one thing I wanted to add here. And if you look at the spin degrees of freedom, when I'm calculating an expectation value, then from the spin degrees of freedom, then this sigma 1 has obviously to be equal to this sigma 1. And this sigma 2 has to be equal to sigma 2 when I'm calculating expectation values, which means that I will get a degeneracy which corresponds to the sum over the different spin values, and that will give rise to a factor of 2 here. So I will have a 2 pi divided by v, and then I'm going to have a summation here over p and k, and q is different from 0. And the spin values, so the contractions which I'm going to have with the spin values, are going to be so that there are only specific possibilities which are allowed. So I will have a phi 0, and then I'm going to have the operator, which now gives me, let me just put up here. No, there's still a sum over spin. Sorry, I was forgetting that one. This is just a constant sigma 1, sigma 2, and then I have a phi 0, and this is going to be calculated with respect to, and now I need to find back my note here. Just a moment, I just need to find back the note I had. Too many different notes here. There is a factor I actually forgot where it came from. Okay, so I see also the time is running a little bit out here. So because I wanted also to say something about the midterm. So the thing I'm going to state here, let me just take this out, and then we will conclude this calculation next week. The thing is that this term here is going to be given by a minus times a constant multiplied with a density, where the density is the number of electrons divided by the volume to the power of 1/3. So we are going to conclude the calculation in the first lecture next Thursday, because I actually wanted to use the last 10 minutes to say something about the midterm here. Sorry, this takes a little bit more time. It's a kind of a boring exercise with integrals, but I actually lost myself in some constants because suddenly I couldn't retrieve where that constant came from. So let's just fulfill the calculations in the first lecture next Thursday. And now let's move over to a short discussion of the midterm, if that is okay. Because I need another lecture for actually wrapping up this calculation of this integral, so that you can see that the final result is given by this quantity here. And that is normally called the local density approximation. And it's used as a first starting point for density functional theory. Local density used in DFT as one of the first approximation, which was done by Kohn and Sham back in '64. And Kohn and Hohenberg got actually the Nobel Prize for having developed density functional theory and computational quantum chemistry. But let's now go back to the midterm. I just wanted to quickly say something about that. There are more details in the lecture notes here. Not that one. So if we go to the first midterm, let's just bring that up. And you will find that under exercises. And The first midterm is here. So I put a tentative deadline on the 21st. Now you guys can collaborate if you want to. I mean, there's nothing which hinders you doing that. So if you want to, and that's often very beneficial when you discuss among yourself, you can hand in an individual answer or you can hand in a group answer if you prefer that. So the first, actually, this is a application of FCI and Hartree-Fock theory. The Hamiltonian is a standard Hamiltonian based on the Born-Oppenheimer approximation, where we only look at the electronic degrees of freedom. So this term here has kinetic energy and the attractive potential from the atomic nucleus. As you would see in descriptions of hydrogen, helium, neon, all the well-known atoms. And then we have a two-electron interaction, which is a Coulomb interaction. So this term has an analytical answer back from atomic physics. So that means that you don't need to calculate an integral here because you simply have it directly. You would just plug that in. Okay. We're also going to make an approximation here that the only single particle states which exist are so-called S waves. That means that the orbital momentum L, which defines the states here, you can see now that when you solve the hydrogen-like wave function, the states will have quantum numbers like the number of nodes, the orbital momentum, which we just put to 0, which means that the wave function is isotropic in space, and it depends only on the radial coordinates. So when you translate everything into spherical coordinates. And these integrals, which you see here, these integrals are then given by analytical expressions, which I actually calculated with Mathematica. And you can do that with so at the end of the here, you will find a table with all the analytical expressions. So these are the integrals which you would need to plug in, but you have to be a little bit careful because these integrals do not include spin. So you need to plug in spin when you're setting up the final matrix element. And then you have to be a little bit careful. And let me quickly say what kind of care you need to exercise. And this goes back to what we discussed yesterday. So let's just look at these specific matrix elements, because when you are looking at a specific matrix element, you are going to have a matrix element of this type, PQ, V, RS, and that will include spin degrees of freedom. So if you think back of what we did now, then if you, in your many-body physics, you're going to include these guys. So this is something which simplifies all your calculations. So that means you need RS minus PQ of V S of R. So if you now look at the some of these combinations, so suppose now that you are looking at two electrons in the 1s orbit, which is one of them. The other one is 2s. And then finally, we have 3s. These are the only single particle orbits which we're dealing with. Which means that in the project here, you're going to have, for helium, this is going to be the ansatz for the ground state. So you will have a spin up and a spin down. Now, if you then look at the integrals, so that table contains the integrals of 1s, 1s without spin. Okay? So in principle, this is particle 1, this is particle 2, and this is particle 1 and particle 2. But you want the anti-symmetrized matrix elements. So when you're setting up the anti-symmetrized matrix elements in the calculations, what you need then is 1s, 1s, V, 1s, 1s. So this is a direct term. So I'm setting up particle 1 and 2 here, 1 and 2. but then you have minus 1s, 1s, v, 1s, 1s, but now you have interchange. So this is something you need to be a little bit careful with when you're setting up the spin degrees of freedom. So the table contains only the spatial integrals. It doesn't involve spin. And this is always irritating because you look into textbooks and they say we omit the spin degrees of freedom because they can be straightforwardly reintroduced. Now, what you have to be careful with now is that this state here can be a spin up, which would be a 1, 0, and 1, 0. And when you're setting up the matrix element, since the interaction does not depend on spin, then we are summing out the spin degrees of freedom. So you need to take into account the case where this one is spin up, but also where it can be spin down. Now, when this is spin up, then this guy here has to be spin down, because this is the way we have made the ansatz. If we have 2 electrons there, then they cannot have the same spins. But when you're summing now, because there will be a summation here, where you sum over spin 1 and spin 2, the spin of particle 1 and spin of particle 2. And you see now that I can also have a situation where 1 is 0 and 1, but then this one has to be 1 and 0. So there are only 2 cases. And that gives rise to a factor of 2 times the integral. But if we look at the exchange term, now we have, if this is 1 and 0, then obviously this has to be 0, 1. But now we have interchange, so 0, 1, and then we have, so this is actually it should be written like that. So they live in their own spaces here. And this is 1, 0, because 1 has now spin up. And then you see that if I try to match this one with that one, that gives me 0. So for this specific case, the exchange term is 0. And what you will only get is 2 times the integral 1s, 1s, v, 1s, 1s. So when you are setting up the matrix elements and you're going to run the calculations, you want to use anti-symmetrized matrix elements. So that table contains only the integral over the spatial degrees of freedom. So you need to add, when you're setting up the calculations, you need to add this constraint. And when you're setting up so let me just bring back this one. In the first exercise, we are going, so these integrals which you have at the end, the analytical expression in terms of the charge, so for helium it's 2, and for beryllium it's 4. These integrals are just over the spatial degrees of freedom. So you need to construct the final anti-symmetrized matrix elements by taking into account spin. So that's a small thing you need to keep in mind here. So with no spin degrees of freedom. So just pay attention to that. So the first exercise, which we have then, if we look at that one, is simply to calculate the setting up the basis. So you find with helium, you have 1s, 2s, and 3s. And then you set up the answers for the ground state in second quantization and define a table of, so this is just setting up the input, the system, the way you define the system. So this is just bookkeeping. So you define particles and holes, you define the Slater determinants, and then you construct also all possible 2 particle, 2 hole states and 1 particle, 1 hole states in second quantization, which you can make in this space. So this is just a simple warm-up exercise. Then here, we want you for helium to calculate the ground state energy. And since you're only going to deal with the 1s as your Fermi level, the states which define a Fermi level, then this will simply sum over the 1s. And that means that the exchange term is going to be 0. So you're simply going to get 2 times that integral over 1s states. So that's pretty straightforward for helium. When you go to beryllium, you need to take into account 1s and 2s. And then the next one is that we simply look at one particle, one hole excitations. And then you're going to count the one particle, one hole excitations, and we want you to calculate these matrix elements. So it's, in a sense, it's just repeating what we've done. And then you can set up the Hamiltonian matrix, which now includes only one particle, one hole excitations and the ground state. And for helium, I think this is a 6x6 matrix, and then you diagonalize. So you need these matrix elements, and then you repeat the same with beryllium. You will have a little bit larger matrix, but it's still doable. And finally, we want you to derive the Hartree-Fock equations and set up the Hartree-Fock matrices. And finally, you can use the code which you have in the notes here, or if you want to write your own, and then solve the Hartree-Fock equations. And then you compare the energy you get with Hartree-Fock with the one you get from diagonalizing, where you only include the one particle, one hole degrees of freedom plus the ground state. So this is essentially just you practicing what we have done till now with Hartree-Fock and configuration interaction theory. So perhaps the worst case is the bookkeeping when you look at these different integrals. Yeah, I'm going to stop here now.